Page 16 is your example problems. If you want some independent practice problems on these, I suggest you try them by yourself in pencil first, and then as I go over them, you correct them or make sure that you are correct. Okay, part 1, exponential functions. Charlene has a flourishing spider plant. She cuts 3 small pieces of the plant called babies. She moves each baby into its own pot with soil. After 1 month, she is able to cut 3 babies off of each of the original babies. She continues this pattern. How many baby plants will she have started after 5 months? Show your work. Okay, so she starts off with 1, and then she cuts it into 3. And then after 1 month, she's able to cut that other one into 3. And then after that, each one of those will be able to be cut into 3. And then it becomes crazy with all of these things here. So you could just follow the pattern. Start off with 1. So after 1 month, she's able to cut 3 babies. Those 3 babies give you 1, 2, 3, 4, 5, 6, 7, 8, 9. And then each of those 9 babies give us 27, 81, and then 243. You should notice that there is a multiplication pattern by 3 here. Okay, so determine if the following tables represent an exponential equation. If they do, find the multiplier. So it's just like how we were finding linear and quadratic. You were going to look for our change in y over a change in x. So all of these x's change by 1. And if it's exponential, there's going to be some kind of a multiplication pattern. So from -5 to -3, we go up 2. So automatically we're adding, so this is not going to be exponential. From -3 to 3, we would add 6. From 3 to 13, we would add 10. And from 13 to 27, we would add 14. So if this were linear, this first difference would all be the same. It's not. Let's see if it's quadratic. That means there would be a second difference, and there is. So this is quadratic. Okay, taking a look at number 8. These all go up by 1. And sometimes, if you don't know what 0.5 would be multiplied to get to 1, you can start anywhere and see if the pattern fits. Like I know that from 2 to 4, that's times 2. From 4 to 8, that's times 2. From 1 to 2, it's times 2. So then 1.5 to get to 1 would be times 2. So yes, this is exponential. Your multiplier is 2. I suggest you try number 9 and number 10 by yourself. For number 9, these are all going up by 1s. We should notice that to go from 1 to 5, we're timesing by 5, times 5, times 5, times 5. So this number 9 is exponential. And our multiplier is 5. Try number 10 by yourself. Okay, so I noticed right off the bat that this is counting by 3s, which is fine. But to go from 4 to 6, you would not multiply, you would add 2. From 6 to 8, you would add 2. You would add 2. You would add 2. So there's a first difference here. So this is going to be linear. So let's talk about our change in y over our change in x. Our change in y is 2. Our change in x is 3. So this is linear. Okay, onto the back for cubic functions, we're going to find the roots and sketch the graphs. Now, the graphs aren't always going to be perfect, but we're just going to try our best here. So Just like with quadratics, if you know that you can take the opposite of the number in parentheses, you can use that shortcut. So I know since there's not a coefficient here, that this first root's just going to be the opposite of -8, so it's +8. That this root is going to be the opposite of -2 and be +2, and that the opposite of that, +3, is going to be a -3. What I'm also going to do is I am going to find the y-intercept just to give me an idea of how that would work out. So your y-intercept, we're going to plug 0 in for x. So f of 0 equals 0 minus 8, 0 minus 2, 0 plus 3. So that would give us -8 times -2 times +3, and that would be 48. So our y-intercept, if we're sketching our graph, would be somewhere way up here at 48. So our roots are 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. So we don't really know all that much about our graph. We know that our roots are at 8, 2, and -3. Take a look at our end behavior. Well, this first number is a 1, which means our graph is going to look like this at the ends because it mimics that of a line. So I know at the end here, this would go up, and over here it would go down. And then we know that somewhere way up here, like 48, is where your graph would cross the y-axis. So all you need to know is it looks something like this. Again, it doesn't have to be perfect. The main thing here is that you're able to identify your tails at the end. So number 12 is -x, x plus 2, x minus 12. So I'll do this one the long way. So -x equals 0, x plus 2 equals 0, x minus 12 equals 0. So divide by -1. One of our roots is x equals 0. Subtract 2 on both sides, x equals -2. Add 12 on both sides, x equals 12. Again, I'm going to find the y-intercept just to get another point to plot. So I would have -0 times 0 plus 2 times 0 minus 12. Well, that would give me 0 times 2 times -12, which is just 0. So we know our y-intercept is going to be here. So we got a root at 0, 0, a root at -2, and a root at 12. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12. Look like this. It's a negative coefficient out front, so it's going to be looking like a line with a negative slope. So all you know is that this should look like this, and this should look like this. And then everything in between, you know this is going to sneak down a little bit, and then this is going to come back up. So the part that I have there in purple doesn't have to be perfect. Okay, now that I've done 2 for you, I suggest that you pause the video and try the rest by yourself. Okay, so for 13, using the shortcut, the opposite of a positive 3 is a -3. And then here, we would have to set these equal to 0. We're going to get 3x equals -8 divided by 3. 2x minus 7 equals 0. 2x equals 7. Divide by 2. So we get -8 thirds and +7 halves. And I'm not going to sketch the graph for this one because they are fractions. But what you do need to know is that your end behavior is there's a +1 out front, so it would your tails would look like that of a line with a positive slope. I'm not going to graph 14 either, only because that is also going to give you fractions. It is a negative coefficient out front, so this would look like a line with a negative slope. So we're going to have 2x minus 1 equals 0, x plus 7 equals 0, and 3x minus 5 equals 0. Adding 1 to both sides, 2x equals 1. Divide by 2, x equals 1/2. Add 5 to both sides, 3x equals 5. Divide by 3x equals 5/3. Subtract 7, we get x equals 7. So these are the 3 roots. If I solved those way too fast, then you need to go back and pause the video and make sure you follow along. This is just solving, in this case, two-step equations. You might need to go back and find a video on the internet to help you with that if you are struggling solving for x. Okay, 15, I'm going to use the shortcut here. We would have 4, -2, and a +3. I'm also going to go ahead and find my y-intercept just to see what it is. So you would have -4 times 2 times -3. That would give us -24. No, I'm sorry, +24, because a negative times a negative is a positive. So sketching the graph. +4, +3, -2. It's got a positive slope, so your tails are going to look like that for a line that had a positive slope. And keep in mind your y-intercept is 24, which is going to be way up here. So as long as you get the basic shape down, it's fine. For 16, these are all whole numbers because there's no coefficient in front of x. So the opposite of a +7 is a -7. The opposite of a -1 is a +1. The opposite of a +2 is a -2. And I'm going to find my y-intercept, which would give us 7 times -1 times 2, which would be -14. So sketching our graph. We're going to cross at -7, 1, and -2. This has a positive slope, so you know your tails are going to be down and then up. We don't know how far up. We do know it'll be way down here, like -14. Again, the major concern is that your arrows are pointing in the right direction. So here's what the back of page 14 should look like and what the front should look like.